Hey, welcome to lecture number 4 in New N302. Last lecture we talked about the mass defect. In other words, we looked at an atom. We counted all the masses of the individual components, and the nucleons and the electrons, and we looked at the mass of the assembled product, and those two ended up being different. And due to the mass-energy relationship there, one is converted to the other. That is what accounts for the discrepancy between the two. So that extra mass that was missing once we assembled it, that got converted to an energy that's holding all the nucleons together. That's the strong nuclear force. Today's lecture is going to continue along those lines. We're going to calculate something called the Q value of a reaction. But there's really not much difference between that and what we just learned about in terms of binding energy. There's a mass discrepancy, and we're going to convert that to an energy. And the Q value is an energy value, but that tells us something more about the reaction, whether it's possible or not, for instance. So we will find those Q values, we'll calculate them, and then we will talk about conservation principles in nuclear reactions. So in any reaction, we're going to term these capital letters capital X, capital Y as heavy particles that have large mass, a large number of nucleons, and then we'll have the lowercase variables X and Y. And when I do this with handwritten notes, I'll do my capital X like you see here, just so that I can distinguish it more easily. But those lowercase variables are going to be the light particles. And this is not light as in photon light. This is just with respect to their masses. We have 2 heavy particles, 2 light particles. So different reactions that we would encounter, there's radioactive decay. We would have one heavy particle that gets converted into another heavy particle, maybe 2, and then some light particles. And depending on what that radioactive decay looks like, we could have 2 or 3 or more different variables on the right hand side of this expression. And so this word spontaneously means it doesn't need any input. It's just going to happen. So the question of how and when does this happen, and the answer to that is it must be exothermic. In other words, it has to release energy as it undergoes that radioactive decay. And we'll spend an entire chapter on, in chapter 4, we'll talk about radioactive decay at length. But for now, what we're going to focus on is what we're going to term binary reactions. And in this case, we've got 2 nuclear particles that interact to form different pair of particles. And this shorthand notation you see here in this, again, this capital X is going to be my large particle, my heavy particle. This is going to be my target. The small particle on the reactant side is going to be the projectile. So for instance, this could be a neutron, this could be an alpha particle, this could be a proton, or some other options. And the equation would look something like this. We have the reactants side. These are the 2 particles that are going to interact and then have the reaction. And on the right hand side are my products of that reaction, a heavy particle and then a light particle. And in a more general form, if we wanted to write this, then we'd have some light particle with a certain number of protons and nucleons. Same thing with the heavy particle on the reactant side. And then on the right hand side of my reaction, I've got my products. And this would be Z3 and A3. And I have a light particle as well, so Z4 and A4. And so there's a few governing laws that we're going to cover here. First of all, we're going to have conservation of nucleons. And we will talk about conditions when we need to put an asterisk on this statement, but for now we have conservation of these nucleons. So if I know what the nucleons are in the light and the heavy particle on the reactant side, then I know that that has to equal the total nucleons on the other side, on the product side. So that's the conservation of nucleons, and I also have to have conservation of charge. And again, we'll talk about other instances later on when we need to put an asterisk on this statement, but again, for now, we'll take this to be truth. So if I know the protons, in the total number of protons on the reactant side, that has to equal the total number of protons on the product side. And these two here, when we say total energy in the nuclear world, we are talking about energy-mass combination. In other engineering disciplines, you'll have conservation of mass and conservation of energy completely independent from each other, but we just can't do that when we're talking about nuclear physics. So we'll discuss these later today. But for now, just know these are the four fundamental governing laws of any kind of reaction. And again, we're going to focus on, for the rest of this lecture and for a good amount of the next few lectures, we'll focus on binary reactions. Binary reactions, I have a projectile, I have a target on the reactant side, so lowercase x, uppercase x, and then I have two products, a heavy and a light product on the right-hand side of that reaction, a heavy one and a light one. So some binary examples here are, what you see here is going to be an alpha particle that is an assembly of two neutrons and two protons, which is the nucleus of a helium-4. This was one of the earliest, or the first, transmutation demonstration, taking this nitrogen-14 to an oxygen-17. This was done by Rutherford in 1919. And then this over here, excuse me, on this over here on this side is hydrogen-1, or just a proton. So I want to look at the number of nucleons, I want to look at the number of protons. So A1 plus A2 equals 4 plus 14 equals 18. That's on my reactant side. The nucleons on my product side, A3 plus A4, is going to equal 17 plus 1, also 18. We're fine there. And then Z1 plus Z2 is going to be 2 plus 7. That's equal to 9 on the reactant side. And then, not surprisingly, Z3 plus Z4 on the product side is going to be 8 plus 1. That's also equal to 9. So we've got those first two conservation statements satisfied. And just going back to the shorthand notation of this, then, which was first illustrated here. So I can write out the reaction like I have done here, or I can use the shorthand notation. And the shorthand notation for this reaction from Rutherford is just going to be I'm first going to put my heavy reactant, and then in parentheses are always my two lightest particles. So my reactant and then my product, both light particles. So this would be alpha P, alpha on the reactant side, proton on the right side, on the product side. and then I put the resulting heavy isotope on the product side. And so that's the nomenclature that I'm going to use that is shorthand for this equation that's provided up above. So another example of binary reactions is here. I've got one neutron and it's interacting with a uranium-235, and we know from experience that has a high tendency to undergo fission. And so this is the primary focus of Chapter 5, Unit 5 in this course. Another one is a neutron capture. And we might see this in some control rods, some cadmium control rods. We've got a neutron and cadmium-113 that accepts the neutron, gives off some gamma energy, but then becomes cadmium-114. And so this is what shorthand would look like there. And you notice a lot of times you'll see the proton call out. In Rutherford's example, we have 2, 7, 8, and 1. You'll see the proton call out dropped in many cases, just because I have the chemical representation of that element there. Therefore I know the number of protons, and so it's a little redundant. But so you might see it, you might not. But just so you know, if you don't see it, then you'll need to either become more familiar with the periodic table or have some sort of resource to identify how many protons we have there. So this would be the neutron coming in on the reactant side, and coming out would be a gamma. And this is 114 cadmium. Okay, another one of interest here. This is fusion. I've got hydrogen 2. This is also known as deuterium. And then a hydrogen 3, which is known as tritium. Those two combine together to form helium and a neutron. And so this would be represented like the following. So I've got hydrogen 3 as my reactant side, quote-unquote heavy particle. It's heavier than the deuterium. But a lot of times you'll see deuterium represented as a lowercase d in that reaction expression. And then I've got a neutron on the other side plus a helium-4. So let's go to a few examples just to hammer this point home a little bit. Our first example we have here, we're looking at helium-4 and nickel 60, and so this helium-4, this is my alpha particle. We want to find the missing product, and then we want to express the reaction in shorthand notation. So I have how many protons? I need 30. And so this chemical formula is going to have 30 as, it's going to have 30 as its value for Z. Therefore, we can go to the periodic table and we can see that is zinc. And then my total number of neutrons is 60 plus 4, or my nucleons, I'm sorry, I need 64 nucleons. And so this will become 63, zinc 63, because I have one neutron on the product side. And so this is what fits into the question mark, into the blank there. And if I want to write this in shorthand notation, then this becomes 60 nickel. I've got the alpha as my projectile, and then the light particle coming out is a neutron. So that's how I would write that. Okay, on the second example, we're going to do the opposite. Instead of starting with the equation, the reaction equation, and producing the shorthand, we are going to start with a shorthand and write out the equation. So we're missing one of the products here, and so we don't know what goes there, but we can start writing this out. We've got a proton, and so we've got hydrogen 1 plus copper 63. Copper has 29 protons, and that's going to produce 2 neutrons, and then some missing product, the heavy one. So I've got 29, 30, I've got 30 protons. And then I need 64 nucleons. So 30 protons. Since my neutrons don't have any of those protons, this also becomes zinc as the one up did above. So zinc, this is 30. And I've got 64 nucleons on the reactant side, and so I need 64 on this side. I've got 2 taken care of with the 2 neutrons, and so this becomes 62. Oops. Okay, so this is our missing product, and that's the reaction. So let's talk about different types of reactions. We've got direct reactions. Those are interactions where just a few nucleons, or maybe even just a single nucleon, are affected. This is going to be more likely at high energies. So greater than or equal to about 50 MeV. We could have transfer reactions where we have like a deuterium coming in and a neutron coming out, or an alpha coming in and a deuterium coming out. In other words, I'm taking some light particle in and exchanging it for a different light particle coming out. We could have scattering reactions, and that is where my 2 products, or my light product and my light reactant, are actually the same, and my heavy product and my heavy reactant are also the same. And so this happens when X equals Y and capital X equals capital Y. In other words, if it's a neutron coming in, it's a neutron going out. And if it's cobalt or whatever, uranium, that's the target, then it remains uranium. And so we have 2 different versions of this. We could have an NN. As an example, this is what's known as an elastic scattering. And the energy, so it's more akin to the billiard balls bouncing off an object. And so the momentum is reduced because I give a little bit to the large target, but I don't change the nuclear makeup of that target. That's basically what this is saying. Or I could have N prime, and this will be inelastic. And what the M prime here represents is it has changed the nucleus to go to an excited state, or away from the ground state. Other types of reactions are knockout reactions. That's where I send a neutron in and I get maybe 2 out, or I could even get 3 out. I could have radiative capture. The light product in this case is going to be a photon. And so this would be an example. This would be a neutron coming in and then a gamma ray coming out. And then I could also have nuclear photo effect, which is the opposite of this. So I could have a gamma coming in. So the light reactant is a photon. So I have gamma coming in and N, or gamma and a proton. This derives its name, photo effect, from the photoelectric effect, which is what we talked about a few lectures ago, where photons of different energies, of different wavelengths, were targeted at this plate with the surplus of electrons, and it was only when the energy of that photon was a certain value that we saw the electrons discharge from that surface. And so it's the same effect, right? I have a photon coming in, and this time instead of hitting the electron, we're striking the nucleus, and it's peeling off a neutron or a proton in that case. So a lot of what we do and analyze, especially as it relates to thermal fission, deals with an intermediate step in these binary reactions. That intermediate step is one that's called a compound nucleus, and this is illustrated here in this figure, where the neutrons coming in and the target is going to absorb, and once it does, it becomes this compound nucleus. So you think of this as it's going to become a new isotope because I've changed the number of nucleons, but it's more than that. It's a new isotope at a higher energy level than it normally would be. And so this higher energy level causes the compound nucleus to distort, and then in the example of fission, then I have separation of fission fragments in this highly excited state, and as a virtue of those two daughter products being formed, you get 2 or 3 neutrons that are promptly emitted from that process as well. This compound nucleus is on the order of 10 to the minus 15 to 10 to the minus 14 seconds, which seems really small, but it's actually large compared to what we'll call the natural nuclear time. The natural nuclear time is going to be more 10 to the minus 21 to 10 to the minus 17 seconds. And so this process is important for us to understand because of those timescales. The fact that it takes orders of magnitude longer in the compound nucleus than it does for these other nuclear processes. And so what happens is it absorbs that neutron, and then it's going to then form and react and do something. But in the interim, it has forgotten how it got to the point of that excited nucleus because of the timescales. And so those initial conditions of, okay, did I just absorb a neutron to become this, or did I absorb 2 neutrons and 2 protons to become this? And it doesn't really know, and it doesn't really matter. There's many different exit paths, is what they're called. One of those is shown here. I could achieve this excited state of zinc 64 through many different avenues. 2 of them are illustrated here. I could have copper 63 and a proton targeting that particle, that nucleus, or I could have nickel 60 and have an alpha particle. If either of those were to happen, in both instances, they become this zinc 64. And the star there is what we use to denote that this is an excited state. This is away from the ground energy level. And so what we see on the right-hand side of this expression, we see 3 different options here, and these are basically the possible exit channels. That's the term that is used. And so we can look at now each of these exit channels and see, eventually at the end of this lecture, you'll hopefully be armed with the ability to look at each of these and see which one's possible, which one's not, and what it would take for these ones that aren't possible to become possible. And so in that spirit, let's go to the examples, to our next one. We've got a proton and aluminum 27 interacting on the reactant side, and that becomes this silicon 28 in an excited state. And there we have that compound nucleus, and we've got 3 different exit channels here that are illustrated. And we want to be able to calculate the excitation energy of that compound nucleus first and foremost. And then next, we're going to want to compare that to the energy required in the 3 exit channels. And so you might think that all of this represents information you don't know how to process. But the reality of it is this is exactly the same as what we've done with the binding energy. The fact that there's a mass discrepancy, and we multiply that by 931.5 to change it from AMU to MeV, to go from mass to energy. But it's the same conceptually. There's nothing different in what we need to do in this problem compared to what we've done last lecture and with binding energy and mass defect. And so the compound nucleus formation here, we need to do that part first according to the problem statement. And so I've got the mass. If I want to look at the with my binding energy, remember my mass defect, I looked at all my components and compared that to the assembled version of that. And so if you replace the word components and assembled version with reactants and products, then hopefully you're starting to make that connection with the analogy between the two that I'm trying to draw your attention to. And so what are my constituents here? What are my unassembled components? So I have a proton, and I've got aluminum 27. And my quote-unquote assembled product is going to be my product of the reaction. In this case, it's going to be silicon 28. So I'll subtract the mass of silicon 28, and I'm just going to call that my change in mass. So when we were talking about binding energy, then we should use the word mass defect. And again, the principles still apply. In this case, I'm just calling it change in mass delta M. And my energy then is just going to be C squared times that delta M. So I'll take 931.5 MeV over AMU, and I'll get the mass of a proton, 10825 AMU. And I come here to my chart of nuclides, and I type in aluminum 27. There's my mass. I have 26.981538. And then from that I will subtract the silicon 28. And so silicon 28 has 27.976927. And if I do that calculation, then I'll find out that the energy there is going to be 11.58 MeV. So that's the first part of our problem, is to figure out what the energy is that brought us to, or what the extra energy that we have now that those two reactants have combined into this excited state of silicon 28. So now we need to start looking at these different exit channels. We have 3 exit channels, and this will be the proton gamma channel, this will be the proton alpha channel, and this will be the proton neutron channel. And so we'll look at each of those now independently. So first, the proton alpha channel. So what I want to do there is make use of the fact that I know I have silicon 28. It's just an excited state, and then I'm going to have silicon 28 in the ground state, is what that means, without the star. And that extra gamma there, it represents the difference in MeV between my ground state and my excited state of that silicon-28. And so for this one, it becomes quite simple. So we have silicon-28 in the excited state, and we have the ground state of 0 MeV, and then we've got the excited state at 11.58 MeV. And as we drop from the excited state to the ground state, then my gamma is released. And so in this case, the energy for the, well, we'll just leave it as energy. So my energy that is released is that extra energy that was in my nucleus causing it to be excited. So then it drops down to the ground condition and then releases at 11.58 MeV. So now let's look at the, oh, that was my gamma channel, I'm sorry. That was the gamma channel. Now let's look at the alpha channel, which is my second one, I believe. Yeah. So with this channel, I've got to take the mass of the alpha particle plus the mass of the magnesium-24, and from that I'll subtract the mass of that silicon-28. So this will be my change in mass in this case. And this is going to be analogous to, if you go back to last lecture, to the separation energy. So I'm asking myself, I have silicon-28, and I'm asking myself, what kind of energy do I have to supply in order to break this up into magnesium-24 and an alpha particle? So last lecture, we just asked ourselves, what does it take to go from the nucleus that I have to one with one smaller amount of neutron or one less proton? But the principles that we applied in that, again, just looking at the change in mass, multiplying it by c squared, 931.5, those principles are still going to apply here. We're just not talking about a neutron or proton. We're talking about a cluster of neutrons and protons, so 2 of each. That's my alpha particle. So, but that's going to be my change in mass, and therefore my energy is going to be c squared times that. 931. Hopefully we're getting that number memorized by now. And my alpha particle, to get my alpha particle, I'm going to type helium-4, and that is 4.002603 AMU, plus my magnesium-24, come back here, magnesium-24, whoops. Magnesium-24 is going to be 23.985042. And then I already have the silicon from before, which is going to be minus 27.9, I'm just reading it off here, 27.976927 AMU. Okay, so I do that calculation, and I get the energy is going to be 9.98 MeV. That's how much energy it would take for me to start with silicon-28 and to break that up into magnesium-24 and an alpha particle. And so the question is this possible? And the answer to that is yes, it is, because I have 11.58 MeV to work with. That's what happened between the reactant side and then my excited nucleus for silicon-28. And so because if I started with silicon-28 and I said, what does it take to separate these? It's only 9.98. Well, I'm starting with 11.58, so this is a possible exit channel. And again, the reason why is because 9.98 is less than what I am starting with at the, and when I say starting with, I'm talking about just this now. I'm looking at just the exit paths. And so what I start with, quote unquote, start with in that scenario is silicon-28 in an excited state with a surplus of energy of 11.58. Okay, so let's do our third and final one. This is going to be our proton-neutron channel. And so we've got similar process. We got the neutron, and in this case it's going to be a silicon-27. Oh yeah. I want the mass of that. And then from that I'll subtract the same thing. What I start with in this case is a 28 silicon. That's going to be my change in mass. And just as before, I've got this 931.5 MeV per AMU. And my neutron is going to be 1.008665. And silicon-27, let's go look at that real quick. It's 26.986705. And then we'll subtract the silicon-28 from that, which we already looked up. And again, don't forget to include at least 6 decimal places. So I do this calculation and I find out this is going to be 17.18 MeV. And so the conclusion here is, again, if I started with silicon-28 and I said how much energy does it take to separate this, to peel off a neutron, to peel off one neutron, that is exactly identical. There's no difference with what we did last lecture on the separation energy. That was the whole premise, like what energy does it take to separate one neutron away from this nucleus. That's exactly what we're doing in this, from the excited state of silicon-28 to this exit channel is exactly what we're doing. And so we find out that that energy is 17.18. And what do we have available to us? Well, it's only 11.58. Therefore, this is not a possible exit channel. But the question is, what would I need to do in order to make that possible? And the answer there is that I could, right now I haven't given any energy to that, to the projectile, to this proton. I'm just assuming that the proton and the aluminum-27 just come in close proximity and somehow magically combine and become silicon-28. And then I have these possible exit paths. And so on paper, all this works great, but we'll find out towards the end of the lecture today that a proton being sent in there's some other, especially a proton being sent into a nucleus. We need to look at a few other factors to see if this actually will happen. But given the fact that it does, then we have 11.58 MeV available to us to go down exit paths. Now the question is, well, what if I gave some energy to that proton instead of having it, assuming it was at rest initially? What if I gave it 10 MeV or 20 MeV? Well, then my available energy for my exit paths now is increased from 11.58 to 21.58 if it were a 10 MeV proton. And so what that does is it opens up additional exit paths. And towards the end of the lecture, we'll come back to this and look at some calculators on some of the web pages that we've showed you last time. So I could increase the energy of my proton to open up this exit path, and there's other exit paths that we haven't included here. Right? We just included 3. There's many more. I could have not countless, but I could have a dozen or even more in some cases, different exit paths that are theoretically possible, but it just depends on how much energy is available to and how much energy that exit path requires. Okay, so let's go back to our final two conservation principles. And again, because we're nuclear engineers, we're combining the mass conservation and energy conservation into a single conservation relationship. And what we're going to do is we're going to start looking at the total energy of each of these. And so my projectile, the lowercase x, has a kinetic energy and it has a rest energy. And so this would be expressed as kinetic energy of x plus the rest energy of x. And then I have the total energy for my target, which is my heavy particle on the left-hand side. And it also has a rest mass. So I got the kinetic energy, I got the rest mass, that's my total energy, and I do the same thing with the products, the heavy product and with the light product. So that expression right there is my mass energy conservation. It's my mass energy balance there. And so what we're going to do now is collect all the masses together, because my rest masses are all multiplied by c squared. So I've got mx, my projectile, plus my target. And I'll move things over to this side. I've got my plus or minus my minus the heavy one. That's on my left-hand side, and I'll move everything over to the right-hand side with kinetic energy that I need to. And so this will be my product kinetic energies minus my reactant kinetic energies. And so this is we've got nothing but mass on one side, and I got nothing but kinetic energy on the other side. And this equation is what's known as the Q factor. This is the definition of the Q factor. And I can calculate this either expression. I could do it with mass multiplied by the speed of light, or I could do it with the kinetic energy if I know the kinetic energies of all my products and reactants. In almost all cases that we're going to deal with, we're going to take this here to be 0. And what that means is that my heavy particle on the reactant side is at rest. I don't have a velocity to it. And you might wonder if that's ever going to be physically realistic. And the answer to that is, well, of course it can be, because we're going to use that as our frame of reference. We're going to put our coordinate axis on that heavy particle on the reactant side. Therefore, anything that's moving is moving in reference to that, and that's how I'm going to quantify my kinetic energy of everything. And so we could just assume, if it's easier to say we're assuming it's at rest versus we're just going to take our coordinate frame to be that heavy particle on the reactant side, then I mean those end up both resulting in the same thing, which is dropping this term out. Okay, so I have 3 different possible reactions that can occur. I can have an exothermal reaction, and that is when my Q is greater than 0. If I get a positive value for my Q, then what that means is that the reactant mass is greater than the product mass. And where did that extra mass go from the reactants to the products? Well, it comes in the form of energy. It's releasing energy. I could have a scattering reaction, which is when my Q value is equal to 0. And that's another way to say that my masses are equal. Or I could have an endothermic reaction, one that is going to require heat. In this case, my reactant mass is greater than, or is less than, less than my product mass. And this Q, when we calculate Q, this tells us how much extra energy we need to supply for this third type of reaction, this endothermic. It's going to come up as a negative number, but the magnitude of that is how much extra energy we need to supply to the reaction in order for it to take place. So let's talk about how Q, this newly defined Q value, how it relates to the binding energy. Going back to lecture number 3. And the answer to that is let's first take the mass of the heavy particle is going to be equal to the number of neutrons in that heavy particle times the mass of my hydrogen, or not my hydrogen, well there's a hydrogen one, but it's electron and proton together, if you remember our binding energy discussion. And I'm going to add the number of neutrons of that same heavy particle times the mass of a neutron. And these two are not going to be equal. They're going to be different by a factor of the binding energy. But because these are masses, now it's got to be binding energy divided by c squared. And so that would be on the left-hand side of this. It would be the mass of the assembled product, of the assembled nucleus, plus the binding energy equals the sum of all the constituents. And so I'm just going to move that binding energy to this side. Binding energy of that heavy nucleus. In this case, I got to divide by c squared. And we're going to do the same with the projectile and our two products. Express them in terms of the number of protons, the number of neutrons, and then we got a binding energy. And so if we substitute that back in for values here, then I get that my Q value is going to be c squared times, I got the number of protons in my projectile plus the number of neutrons in the projectile minus that binding energy of the projectile. And then I've got the same thing for my target, which is my other reactant, times mass of hydrogen plus number of neutrons in that heavy particle. And then I've got the stuff on the product side. Oh, I've got my binding energy too. I can't forget that. Binding energy divided by c squared. So that's everything on the reactant side. And now I'm going to subtract everything from the product side, because that's what I do in this equation here. I subtract my and capital My. So this will be z y mh minus ny, the number of neutrons. In this case, I'll do plus the binding energy. And same thing for my light particle on the product side. Mass of the neutron plus the binding energy of y, c squared. And so what does this look like? I've got mh, combine those together, I've got zx plus z capital X minus zy and z capital Y, plus the mass of the neutron times the number of neutrons on the reactant side minus the number of neutrons on the product side. I don't have a bracket just yet. But then I've got all these binding energies. Binding energies of Y plus binding energy of my heavy product minus the binding energies of my reactants. And what you'll see here is that we can greatly simplify this because of those first two conservation laws that we talked about earlier in this lecture, and that is that my total number of protons has to remain the same, my total number of nucleons needs to stay the same. And the inference there is that also my total number of neutrons needs to stay the same. And so because of that, this sum is going to go to 0, and this sum is also going to go to 0. And so we're left with the Q value is just going to be the sum, and then I multiply my c squareds through and I cancel out all the c squareds, but a sum of the binding energies. So if I know the binding energies of my two reactants and I know the binding energies of my two products, then I can easily calculate the Q value as just the sum of their values here. Okay, so let's go to the next example. We want to calculate the Q value of the exit channel, the PN exit channel, what we saw on the previous example. And so just as a reminder, this is what we found for the energy required to create that from a silicon-28. But we now want to kind of remove that intermediate stage, and we just want to look at the products on one side and the reactants on the other side. So we'll use the definitions that we've developed so far to calculate those Q values, or that Q value. And so this is our reaction here. Again, we're not ignoring it, but we're just taking that intermediate, because the energy is just kind of moving around and getting exchanged. We're taking the initial reactants and the final products. And the PN channel would be silicon plus a neutron. And so I'm going to calculate, we're going to calculate the Q value, and then we're going to look at the magnitude. We should have something that ties back to this number here. I mean, we haven't used any trickery that should give us a different understanding of the physics here. And so we'll go back and we'll look at that and compare it. And so my Q value, I'm just going to use the balance of masses here. So I've got my mass of the proton, I got the mass of aluminum, and then I'll subtract the mass of the neutron and the mass of the silicon-27. Mass of the proton, 1.007825. We looked all these up before, so I'm just going to write them down. 29.81538. And then the mass of the neutron, 1.008665. And minus 26.986705. And my Q value here, if I do the math, becomes negative 5.60 MeV. So let's think about this for a minute. Where are we getting a negative 5.6 from? Or why? How do we rationalize the fact that we have a positive number and it's a 17 here, and we get a negative number and it's 5.6? So I'll draw your attention to what this number here represented, 17.18. Just as a reminder, that represented the energy required to go from the excited state to a state where we've split off an alpha particle, and then we have silicon-28. But we started that analysis with 11 and some change, 11.58 to be exact. That's what we started with, and we're saying here we need 17.18. So the question is, how short are we? And if you take those two numbers and subtract them, 11.58 minus 17.18, And guess what you get? You get negative 5.6. And so if we take 11.58 minus 17.18 MeV. So without doing the sub-analysis steps with the compound nucleus, we can just look at the beginning products and end products, and now we have a measurement for how much energy it would require for us to go from the reactants to the products. And in that case, it's negative 5.6. And so what that means is that we need to supply, that proton needed to have an energy of 5.60. It needed to have a velocity that corresponds to an energy of 5.6 MeV. And if it would have, then this exit channel now becomes open to us. It's not impossible. Okay, so we arrive at the same conclusion and the same solution, even the same magnitude of numbers in terms of what we needed to do to that alpha, or the proton, in order to get this reaction to take place. So the last part of this question asks us to look at the binding energy. And so I'm going to calculate this. We're going to look up the binding energy for, now let's do this. Q equals the binding energy of 27, silicon 27, plus the binding energy of a neutron, minus the binding energy of a proton, minus the binding energy of aluminum 27. So we can get rid of these two. The binding energy of a neutron and the binding energy of a proton are both 0. Binding energy by definition was how much energy does it take to hold these protons and neutrons together compared to having them all split up. And so if they're already split up, we don't have any binding energy to worry about. So let's go look up the binding energy. This was part of the data that was available to us. So let's go back here. We have silicon 27. The binding energy, this reports it in binding energy per nucleon, but we can use that. We'll just multiply that by the number of nucleons. And let's write that down. 8.1244. And that's going to be MeV per nucleon, so I'm just going to put A there. And I'm going to multiply it by the total number of nucleons that I have, which in this case is 27. This is silicon 27. Yeah. And then I'll subtract from that the binding energy of aluminum 27. Come back over here and look at that value. The binding energy there is going to be 8.331553 MeV per nucleon, and I also have 27. Oops. I also have 27 nucleons in this. And if I do that math, then I get, unsurprisingly, I get minus 5.6 MeV. And so it's the same, and that's good it's the same because that's what we derived. That's what we expect it to be. So let's go back to the lecture and start talking about momentum conservation. So this Q value is what came out of our discussion of the mass-energy balance, the mass-energy conservation. So now let's talk about our fourth and final conservation, which we started off at the beginning of the lecture. And let's talk about conservation of momentum. So the linear momentum must be conserved here, and what that means, in talking about this, we're going to first take the easiest case, and that is where we take the kinetic energy of both reactants, our target and our projectile. We're going to take those kinetic energy to be 0, which means they're both stationary. And the question is, well, when could we ever see that? And the answer is, well, that's what happens when you have spontaneous radioactivity, when you have spontaneous decay. You have a nucleus that's just sitting there, and in this case, there is no projectile. It's just the target, and then it spontaneously decays into a daughter product and an alpha particle, for example. And so what Q would be left with is, since both the kinetic energy of the target and the projectile are zero, then the Q expression in terms of kinetic energies is just the following. So my Q value has to be the sum of the kinetic energies of both the products of that reaction. And so we'll just make a note here. The important example of this is decay. And so I've got a heavy nucleus. This is meant to be a lot of nucleons here. And I'm going to eject an alpha particle. And what we want to do here, in order to get the entire picture of the conservation of momentum, of this linear momentum, we need to know the energies, we need to know the directions. So in what direction is this alpha particle going to be ejected from this heavy nucleus? And the answer in this example is that it has no preferred direction at all. So the term there is isotropic. It's an isotropic emission of the alpha particle. There's no way that we could ever predict exactly which way it's going to go. It has the same likelihood of being ejected in any direction. And so in that case, the linear momentum is a vector, and those two have to be equal. In other words, if my alpha particle is ejecting vertically upward, then the momentum imparted to the remaining nucleus is going to be in the opposite direction, going to be downward. And if the alpha particle ejects in the positive horizontal direction, then the remaining nucleus has to also be in the horizontal, in the opposite direction. And so the momentum there needs to be conserved. And since there is no preferred direction, and there is no projectile in this case, then my linear momentum balance is like you see here. What we're going to do is we're going to square both sides to get it into a scalar form. And after we square both sides, we're left with the following. So this is now no longer a vector. And if we look at if we keep ourselves in the non-relativistic realm, which is a good assumption for the scenarios we're encountering today, then my kinetic energy of the smaller of the two particles, so in this exact example, it would be the kinetic energy of my alpha particle, would be 1/2 mass of that lighter particle times its velocity squared. But in terms of momentum, this is velocity y squared times the mass of y squared. Momentum is velocity times the mass, and so the square of that becomes the square of both sides. And so I can equate this. So the kinetic energy of that smaller particle is just going to be 1/2 times the momentum divided by the mass. And I can do that same thing for the kinetic energy of the larger particle. Kinetic energy of capital Y is 1/2 times its momentum over its mass. Momentum squared over its mass. And so taking this expression here, saying that the square of my momentum has to equal the square of my momentum of the other, then I can come up with this relationship here where I say that since my momentums are, the square of them are equal, then this is going to be equal to 2 times the kinetic energy times the mass of one has to be equal to 2 times the kinetic energy times its mass of the other one. And so my 2's cancel out. And I'm left with an expression now I can solve for the kinetic energy of my light particle or my heavy particle. I'll solve for the heavy particle here. And this is just going to be the kinetic energy, its relationship to the lighter particle is just going to be the mass ratio of those two as well. So we've got my over m capital Y. And so what we're going to do is make use of the Q value expression. And the Q value expression that we're most interested in is one that has the kinetic energies on the right hand side. So in terms of Q, then Q is going to be kinetic energy of the products minus the kinetic energy of the reactants. But again, we started this off by assuming these were 0. And we're going to take this now and substitute that in here. And so now I can relate the kinetic energy. If I know the Q value, I can ultimately find the kinetic energies. That's what we're after here. We're after knowledge of the kinetic energies and knowledge of the direction. In this particular example, this case 1, where we assume no kinetic energy for either of the reactants, then it doesn't make sense to talk about direction at all, because if the direction of the light particle is this way, the direction of the heavy particle is that way, and it's just as likely to happen in any direction, isotropic emission. And so we'll do this again for a second scenario, one where we no longer neglect the kinetic energy of at least one of those two reactants. But so I can now find the Q value up until the last example. I can find the Q value one of 3 different ways. But I don't know the kinetic energy, so that's only 2 ways. I could do the binding energies, or I could do the mass. And now I want to use the Q value to help me find those kinetic energies. So my Q value is going to equal, I'm going to substitute this in here, so I've got my kinetic energy of my small particle multiplied by that mass oh, I put that in the wrong one, didn't I? Yeah. This is, oh no, that's right. That's right. So I've got this times the mass plus 1. And that is the expression for my Q value. I just solved this for my kinetic energy now. Since I know the kinetic energy, or since I know the Q value, I can use that to solve for the kinetic energy. And that's going to be no, I did something wrong here. Oh no, I made a mistake here. This needs to be capital Y. And I could then solve for the kinetic energy of the large product, and that's going to be my plus my. And so what you find here, since the Q value is the same for both of them and the denominator in this expression is the same, what you find is that the only thing that's different is these two masses up here. And so the smaller of the two particles actually has a larger kinetic energy than does the larger of the two particles. So what happens now when we no longer neglect that kinetic energy of my reactant? And so we're gonna employ the same reasoning behind what we did earlier, and we're still going to take the kinetic energy of the larger of the two, so my target of the reactants, I'm going to let that equal 0. My kinetic energy of that's 0. So either it's very large and moving slow relative to this, or I just put my coordinate axes there, and therefore I have 0 velocity. So what am I going to do if that kinetic energy is not 0? So I've got my small particle targeting the large nucleus, and I could have something here that's my large reactant, and then I have a small large product, and I have a small product, y. And these angles here, I'm interested to know at least know those angles, or be able to take from those angles. If I know those angles, then I can calculate the kinetic energy. So in this problem now, I've got a number. The unknowns are my kinetic energies. I'm assuming I know the one coming in though. So knowns is going to be, generally I know the kinetic energy of my projectile, and I'm going to assume that I know the masses, and in this case that I know that angle. And what I want to find now are the kinetic energies. Now, do we know the angle? The answer to that's probably no, but we can express my kinetic energy in terms of that angle and see what kind of magnitude change it has from 0 degrees to 90 degrees or 180 degrees. And we're still going to assume that the energy of my target nucleus is 0. And in this case, we drop the k's, right? So just note that Ex equals really the kinetic energy of x, and the same thing for y and capital X. So if I go through the same steps that I did before, and this will be one of your homework problems, if I go through the same steps as I did before, then I arrive at the following solution in terms of Ex, phi, that angle, and then my masses. So if I want to solve for Ey, for example, then Ey raised to the 1/2 power, so I'm going to take everything on the right hand side of this expression. I'll have to square that. We've got mx, my, Ex to the 1/2 cosine of phi, plus the sum of my two products. And it's this same quantity here, but I just square it. So this might look familiar or show some resemblance to the quadratic formula. That's exactly what you're going to find out you get. So this is b, the opposite b plus or minus the square root of b squared. And then the rest of the stuff in this bracket is going to be my over my plus my times my minus mx over my times the energy of that projectile, and then I've got my Q factor. And so the question here is, well, the question you might have is, where is the kinetic energy, or where is the kinetic energy of my target is 0? We've already talked about that. But what about the mass of my target? I only have the mass of my projectile and the mass of my two products. I don't have m capital X in here anywhere. And so you might be wondering why that's the case, and the answer to that is it is in there. It's just built into this Q. And so that encompasses that. If I change the mass of that target, it's going to change Q. Therefore, it is in there just indirectly. So that's going to give me my kinetic energy for the smaller of the two products, and I use that to find. I just use my expression for Q. After I know the kinetic energy of my smaller of the two, then I can use that along with other things that I know in order to find the kinetic energy of the larger particle. Okay, so let's go to our last example here. We want to calculate the neutron kinetic energy in the following. So that's this one, that's EY. The neutron kinetic energy is EY. In the following reaction, when the initial, this is going to be my alpha particle, is 5 MeV, so I've got Ex is 5 MeV, and the neutron is emitted at an angle of 0. So I've got phi equals 0. And I want to repeat this for different angles. And this is commonly what you will do just to gain a picture of how influential that angle is going to be, because it's not that you have that before you run the experiment, but you want to see after you measure energies to see if it fits within this angle or that angle, that sort of thing. Okay, so we can either plot this, or in this case we're just going to calculate that, and there's really nothing to this other than first finding the Q value, and once you have the Q value, you have the masses, you have Q, you already have Ex here, and so we're going to use all that information in this somewhat hairy equation, but we can do this quite easily. Let's just literally plug that in and calculate it out and see what you get. So let's first do the Q value expression, and what we're going to do there is we'll just do the sum of the masses here. So we've got the mass of helium-4 plus the mass of beryllium-9 minus the mass of my products here, so that's going to be carbon-12 minus the mass of a neutron. All right, so 931.5 MeV per AMU. We've done this many times now. And to that I'll look up the beryllium, 902.183 minus, this one's easy, right? Carbon-12, the mass there is 12 AMU, minus the neutron, 1.008665. Those are all AMUs. And so for my Q value, I get 5.7. And now I want to use that in this expression. So let's go back and get that expression really quick. This expression here is what I want to plug that into, and I've already done this in Excel, and then I'm going to show you some other tools you can use that will be helpful to you in all these calculations. And it's in your best interest, by the way, throughout the course of the semester to be building yourself tools. So what I'm going to provide to you today, and you can find other resources for this, by the way, but what I'm going to provide to you today is a text file that lists the number of protons, the number of neutrons, and the atomic mass. And so it's in your best interest to be building some tools along the way that run these calculations for you, rather than each time you're required to do this, having to look it up with these one by one through these different resources. They're there, they're available, and you can trust them. It's just time consuming, and if you're needing to do this multiple times, it's going to be in your best interest to automate that. And so I'm giving you the atomic mass units. You just need to build yourself a function that looks up, that as inputs it takes Z and A, and the output of that will be AMU. Okay? And it's basically just a lookup table, because that's exactly the data that I'm giving you. So let's go to first Excel, and here's my calculations. So there's the mass of my alpha particle. Here is the mass of my heavy nucleus, and here is the mass of my heavy product. That's the carbon, and I've got the neutron here. So this one's beryllium 9, carbon 12, neutron, and then alpha particle. And here I just calculate the difference in those masses, as I did just a minute ago, and that's my Q value. And this is part of the inputs, or this is a known quantity from the problem statement. This is a known quantity from the problem statement. I'm just converting this into radians here. There's nothing special there. And this is where I decided to use the fact that it's opposite of b plus or minus b squared. It's this quadratic formula. So that fraction 1 is my b. So if you go back to the expression here, then what I'm talking about is this. I'm calling that b, because this is nothing more than b squared. And so that's what this fraction 1 is the value for b. So I've got mx, my, the ex, all square root, times the cosine of the angle phi, divided by the sum of my two masses on the product side. So there's that, and then fraction 2 is what, if you come back here, then fraction 2 is this one here. That's just a ratio of my, go back here, so my ratio of the large mass of my product over the sum of my two masses. And so then otherwise this equation, at least in Excel, is going to be a bit hairy, lots of parentheses, and I'm prone to make mistakes, so this is going to help me kind of troubleshoot that and see where I went wrong. So this is then the b plus or minus the square root. I'm just using plus in this case. We'll do the minus in just a minute. B squared, so that's f1 squared plus f2 times my minus mx divided or multiplied by the q, or the e of my projectile, energy of my projectile, divided by the mass of the heavy product. And then to that I add my Q value, and I'm going to square that overall, because on the left-hand side of the expression here, I've got EY to the 1/2, and so I've got to square the right-hand side. And so this is what I get for, I guess I got to change that to 0. This is what I get for if my phi was 0, this is what I get for E, the kinetic energy of my light product, and this is the kinetic energy of my heavy product. And it's not surprising, again, that this one is bigger than this one. It's going to have a lot more velocity to it. And then this is calculated just with the expression that I had a minute ago, just the Q value minus the EY, and then add that to that. I'm going to add my kinetic energy of the projectile. So then all I got to do is change this to different values, and I can't remember the values off the top of my head. Let's go back and look here. So we got 5 degrees, 5, 20, 45, 80, and 90. But I can come here, and now this little calculator I have, and you don't want to do this in Excel, by the way. There's not anything preventing you from doing that, but I would recommend you use Python. I'm going to show you some MATLAB scripts. There's really not much difference between doing it in MATLAB and doing it with Python, other than the cost. Python is free. But all I need to do here is then just change my degree, and I can look at what happens to the energy. And so let's start back at 0. this starts out high at 10.6. This is 0.12. And as I go to 20 degrees, let's say, this is decreasing, and this one is increasing. And as I go up to 90 degrees, I still see that. My kinetic energy has decreased on this light particle and has increased in the heavy particle. All right, so let me show you real quick in MATLAB. So what I'm not going to show you is the code, the underlying code that is calculating this. So this is code that I wrote. This is my lookup function. So I have the inputs to this being Z and A, and its output there is going to be in this file here. My AMU function is going to then just output the mass in AMU. So there's the mass of my projectile, the mass of my target, beryllium 9, so that's 4 and 9. The light product is going to be 0 and 1, that's a neutron. The mass of the heavy product is going to be 6 and 12, that's my carbon 12. Just let me show you how this looks like if I do AMU 6, 12. I should get a value of 12, yeah. And if I do 0 and 1, then that is the mass of my neutron. And if you're scared that I'm not collecting enough digits, that's just how it displays it here. But if I take this and I multiply that, you'll be able to see it a little bit better. So I've got lots of digits of precision there. But here's all my inputs in this file then are just the number of neutrons and number of protons, and the number of nucleons in each of the 4 masses that I'm dealing with here. The other input is my projectile kinetic energy, and then I use that to calculate Q. I've got my 931.5 here to calculate my reaction. And here's where I can step through different angles. And so I'm using the exact 6 angles that I've been asked to use for this example here. Then I convert that to radians and initialize some vectors. You don't need to know that. But then I run through this vector of angles. So I've got a vector now, 0, 5, 20, 45, 80, and 90. And I'm going to go one by one through those, index 1 through index 6. And I have this function KEY now that I created, and that is nothing more than what I did in Excel. So there's my F1, there's my F2, and I calculate my value here based on that function, then I square it to get my overall output. So that's what that does, and then I calculate my kinetic energy of the large product, the heavy product. And then I wanted to plot the results. So let's look at the phi versus the kinetic energy of my light, and then phi versus the kinetic energy of my heavy particle. So as I run this, so I'm starting to see exactly what we were noticing in the Excel analysis, and that is I start high with my kinetic energy of the light particle, and then that decreases as I increase if the angle were increased, and then my kinetic energy of this one increases. And as I take this, and maybe I want to do 0 to 180, in fact, and we'll go in units of 5 there. So let's run this again. And you start to see behaviors of this, of the resulting energies for both the products as a function of what that angle might be. And so if I measure my kinetic energy of the light particle and the kinetic energy of the heavy particle as whatever this value is, 7.67, and this one is 3.02, then I can infer that the angle, that phi, was 110 degrees, is what that means. So this file here, this is what you're going to be given and what is posted on Canvas. So you see the first column is my neutrons, or my protons. My next column is the nucleons, so that's the protons and the neutrons together. And then this final one is my AMU value for that nuclide. So again, you have this text file. I will leave it up to you to create your computational pieces along the way. And you're going to want to do this throughout the semester. And if you listen to my advice and do this along the way, then your take-home final exam is not going to be the worst thing ever. And if you don't heed that advice and don't build these tools along the way, it's going to be very, very difficult for you. So that's the first set of data that I'll give you. I have a handful of others I'll give you throughout the rest of the semester, but be building these calculators along the way. Now, there are some calculators available through trusted sources, and I'll show you one of those right now. And then we're going to compare that to one of the early examples that we did during this lecture. If you come back to the Brookhaven, National Nuclear Data Center here, and you come up to the structure and decay here, you'll see there's a tools section here, and there's a Q value calculator. So I can type in a nuclide here. So let's do 12 carbon. So you see it provides the AMU. It provides the, we'll get into these later in the semester, but here's the atomic mass, or the binding energy divided by the atomic mass. And so you can get information here just like you were getting in this Korean one that we've used, or any of these other ones, right? It's the same underlying data sets, just different presentation. So you're welcome to find the one that you like. But in this, if I click on the reactions button, let's go back to the early examples that we had here. In fact, let's do this one here. So in example 4.3, I've got a proton, that's my projectile, and the target is aluminum 27. So my target, 27 aluminum, and my projectile is a proton. And in this case, we didn't have any. This is the MeV of the proton. And in the example, we didn't have any. We weren't given that information, right? We talked about, well, what would we have to do to that proton in order to get it to go down this reaction path or that reaction path. Yeah. Okay, so it gives me three different options. If we look at this first one, I've got silicon 28 and gamma. And so this is 11.58, so 11.6, 11.58, let's just keep it at that. This is KeV, notice, and so if I change that to MeV, I get 11.58. And if we go back to the very first part of that, we looked at the gamma channel, right? The proton and gamma channel. And this was what we found, was 11.58 MeV. And so what this represents is, in order for you to go down that exit channel, this is the Q value for that. Now, what were the other ones we considered? The next one down was magnesium 24 and alpha. Going back to this Brookhaven calculator, there's my 24, magnesium 24, there's my alpha. I get 1.6 MeV. So what is the difference between, going back to my solutions here, I said that I needed 9.98 MeV. Well, what are we supplying? We're supplying nothing on the proton end. The proton end. We're not. It doesn't have any MeV, but we are getting 11.6, 11.58 from that intermediate state where we have the excited silicon, and that's what's available to us to go down these exit paths. And so if I go down this exit path, I would have 1.6 left over, because I was supplying 11.58 and I needed to supply, and I needed 10 to go down this exit channel. With 9.98, it was about 10. So there's your 1.6 MeV. And then this one here, I've got aluminum 27 and a proton. So I started with aluminum 27 and a proton, and I ended with it. I didn't change anything, and so there is no Q value associated with that. That's an elastic reaction. Okay, but we can see now if I take, notice it didn't list any of the other ones, like the fourth one that we had there was silicon 27 and a neutron. That was the exit channel. And so we determined that wasn't possible in our analysis, and it doesn't report it here because it's not possible. And so if I bump this up, it told me I needed 17.2 or so MeV, and I had that 11 or so available. So what I need extra is 5.6. And so if I change this to 5, that shouldn't be enough, right? I needed 5.6. Unless I supply at least 5.6, I'm not getting there. And now you see that an extra path, an extra exit channel has opened up. If I supply at least 6 in that regard. So, okay, so what you do in this case, you can take these Q values, and if you want the total energy, you can take the Q value and add to it this value of 6 MeV. And so this exit channel is available to me. I take negative 5.6 and I add 6 to it, and so I've got a little left over, some change, which is available as extra energy. In this case, I'd go 1.6, and I'd add to it additional 6 and so on. But I could take this up to 10 MeV and see if there's any additional exit. So we've got some additional exit channels now. So I could do neon 20, and I get 2 alpha particles, or I could have magnesium 26 and I get 2 protons. So I send a proton in and I get 2 protons out. So that would be a good reaction if you're looking for proton generation. Okay, and so there's calculators available to you, and you don't need to feel guilty for using them. You're welcome to use them on the homework unless I specify use the mass, then look up the AMU. But I will say that again, that it is in your best interest to take this data file and start building in at least a lookup function so that you can then create other code to then make use of that lookup function. Because every piece of code that you have from here on out is going to need the AMU. And so if you can right now build that lookup table, build that function into it so that the inputs are Z and A and the output is AMU, then that's going to help you with Q value, that's going to help you with kinetic energy, that's going to help you with everything that we're going to do from here on out. Okay, well that concludes this lecture. We'll see you for lecture 5. Thanks.